Welcome to No Face Man's STT class. Have you ever heard of STT? Do you know what it is? STT is the abbreviation of spin transfer torque. But wait, what is spin? Here is an electron. Electron has two states, spin up and spin down. Can we control spin states? Of course, yes. Let's see how to switch spin states of electrons. In 1996, John, from IBM, proposed a feasible solution. That is spin transfer torque switching. When electrons with misaligned spin pass through a magnetic material, the mismatch between them gives rise to a small twisting force. We call it a torque. A dense current can generate a torque large enough to flip the magnetization direction of the material in principle. How we apply this theory to engineering.
Now we're going to introduce the most important part in the STT MRAM, the MTJ structure. It's called magnetic tunnel junction. As you see, there are three parts in this structure. The first one is free layer. There are two directions of spin in this layer. In the middle is insulating layer for dividing the free layer and the bottom one. The last one is fixed layer. This layer only has one direction of spin.
What happens when electrons move from fixed layers to free layers at antiparallel state? After spin-up electrons pass through fixed layers, there are no seats for them in free layers, so that they are scattered back. It is why antiparallel magnetization generates high resistance. Then, we define antiparallel as 1, parallel as 0. When we want to write 0, the electrons flow from fixed layer to free layer, then flip electrons with opposite spin. When we want to write 1, the electrons flow from free layer to fixed layer. The electrons with same spin pass, and those ones with opposite spin will be reflected by fixed layer.
The overall writing process is like this when we write 0. Magnetization in fixed and free layers are antiparallel at the beginning. Majority electrons are scattered at first. If large number of majority electrons pass through, they will flip magnetization direction in free layers finally. Magnetization in two layers become parallel. That is successfully writing 0. Vice versa. After enough minority electrons pass through free layer, the torque is large enough to flip the magnetization direction in free layers. Therefore, antiparallel magnetization generates high resistance and represents 1. Because we use minority electrons to write 1, we need higher current to make it.
STT MRAM is known as an universal memory device because it combines the advantages of SRAM, DRAM, and flash memory. It is non-volatile and has random access memory without moving parts. MTJ is the key building block. It uses spintronics to write magnetic bits. Here are the advantages of STT MRAM. It combines the advantages of various types of memory, improves performances and reliability, lowers cost and power consumption. Of course, there are some disadvantages, including higher write latency and energy. The latency and current depends on the polarity of the data being written. Therefore, there still exist some challenges in the materials we use. STT MRAM techniques have been improved since invented in 1996. Later on, within 2 decades, scientists came up with other innovative solutions to make STT MRAM better, like using magnesium oxide as barriers to ensure high magneto-resistance ratio, giving more precise reading. Also, perpendicular tunnel junction make nano-sized junctions possible, thereby increasing the density of MTJ devices. Now, do you understand more about STT? If you like our video, please click like and support us. Thank you.